Good evening. There's nobody here right now, but I'm going to start the session. I'm sure people will show up. Okay, I've turned on desktop sharing and recording. Let's see. Let's put up the agenda. I'll ask questions when people show up. I want to discuss Chapter 6. Hi, Steve. I just kind of started. Can you see the desktop okay? Very good. Did you have any questions on Chapter 5? I was going to just do a quick review. Okay. Well, the whole idea is to schedule the CPU effectively. There's several different algorithms have been used over the years, and it depends on the system too, what style of system. First come, first serve, typical. Not very efficient, we showed that. Shortest job first, basically it's optimal. You want to schedule, but it's almost next to impossible to determine which or how long a process is going to run on the CPU. Priority. There's user and operating systems priority. Hi, Albert. I was just reviewing Chapter 5. You have any questions on Chapter 5? Very good. The issue with priority is the concept of aging. It's possible that a low priority process will not get the CPU. So it starves. And aging is a way of bumping up the priority. Let's see, round robin. You have a time quantum. Each process receives the time quantum. Then it gets preempted and placed back at the end of the round robin queue. Multi-level feedback queue I wanted to spend a little more time on because I wanted to finish our sample Word document that we started on Tuesday. I have a question for you guys. Could you tell me what a preempted operating system is? Can you kind of type it out in a few words what a preempted operating system really means? Hi, Bale. Okay, once again, the question is, yeah, go ahead. What is a preemptive operating system mean? Yeah, I see two people typing. I'm reading your answers. The concept is that the running process can be preempted by various reasons, and I think Albert specified some of those reasons. Whereas a non-preemptive type operating system allows the process to continue until it relinquishes the CPU voluntarily. You could still handle interrupts, but the idea would be it would handle the interrupt, and then the process that was running would get it back, would get the CPU back. That's the concept of non-preemptive. So yeah, it's possible that this operating system gets interrupted, the operating system does some stuff, but it reschedules the process that was running. Whereas preemptive is the process that was running could get interrupted by any number of events, and then the dispatcher would decide to preempt it and put another process in its place. Is that clear? Okay, good. Okay, I went over these. The multi-level feedback queue document we worked on last time. First, let's look at the rules that we were using. All processes enter the ready list at level 0 and preempt any lower level running processes. A preemptive process is placed at the beginning of the level at which it was at with the remaining quantum as its new quantum size. All levels' quantum size increase as the number of levels increase. And for example, level 0 quantum size is less than level 1, less than level 2, level 3, etc. Any process that times out at a level will be placed, any process that times out at a level will be placed first come, first served in the next lower level. So if L1, process running in L1 times out, it will go into the back of L2's queue. But L2 is going to give it more CPU. At the lowest level, whatever the lowest level is, if a process times out, we place it round robin at that level, until finally it requests service or terminates. And every time it requests service or terminates, we bring it back at level 0 and start the whole process procedure over again. Any questions on how the flow works? Hi, Mega. I asked you guys to work on it. Did you guys complete the document? It was hard, but you did. Good. Well, did you compare it to the completed solution I showed? Oh. Oh. Okay. Yeah, I want you to understand it, because this problem is exactly the problem you're going to see on, well, not this particular, the set of circumstances will be different, but the problem will be exactly the same on the next test, and it's worth 5 points, so it's worth understanding. We left off on our sample right here. When A got the CPU right here, and it did one of its units, and it needs another unit to have its 4. Well, it's at level 2. E preempted it because E is coming in at level 1, a higher level. So we preempt it and put how much quantum is remaining for A's level 2. At level 2, it should have received 3 units. Sure, Dale. From 4 to 5? Here's 4, here's 5. Okay. Well, the rule was that when it times out at a higher level, it goes first come, first served at the next level, which means it would fall after D right here. It would fall after A, actually. D would fall after A because D got its 2 units right here. D got its 2 units, and at level 1, that's how many units is allowed. That's how the quantum size. I mean, why did I set the quantum to 2? It's just an arbitrary number. Each of these levels, the quantum size for each of the Q levels, I picked 2 units for level 1, 3 units for level 2, and 4 units for level 3. It's just an example. In real life, this could be 10 milliseconds, this could be 20 milliseconds, and this could be 30 milliseconds. Okay, and then I wanted to illustrate each unit, what the queuing system looks like at each unit. So unit 1, we have this. Unit 2, we have that. A times out, so we push it down to the next lower level, and we fire up D because it's at level 1. And D goes for 2 units, times out at level 1. We place it at the back of level 2, and then we start up B. B only needed 2 units. Now at level 2, the quantum is 3. Well, it used 2 because it only needed 2 of the 3. So it finished, or it requested service or something. But it gave up the CPU. Then we start the next guy, which is A, and at this level we would give it 3 units. Well, it got 1 of the units at unit 7. I want to stop a second. Is that clear for everybody? Okay, if not, I'll try explaining it a different way. What happened was E entered, so E might have had a I/O completion interrupt occur, right? Which would then place it in the ready state. It was waiting, or block state. Now it's ready to execute, and it always enters at the first level, level 1. And when it did, it preempted A. So we have E running, but when we preempt A, we put it at the beginning of the queue, right here, that it was at, and we keep track of how much quantum it's remaining. Not first come, first serve. It did come first. A is ahead of D in this queue, in level 2. It's not coming back. It's basically it was it was launched onto the CPU at this level. When it got interrupted, we placed it back at the beginning at this level. That's all, because it never finished its quantum, and we want to give it its quantum. If we stick it behind, now we're, kind of saying, well, you don't deserve the quantum you got. We're going to push you behind. So we're not going to do that. We're going to push them in front, and we know at level 2 is 3 units. He had one of the units, or she had one of the units here, so it has 2 more units of quantum available, and we make a note of that. So E only needed 1 unit. It says here, E will enter at level 7 after 7 CPU units requiring 1 unit. So it's done. So what should happen next? Yeah, we DQ'd E, yes, but what's executing? We always want to show a process executing. What would be given the CPU? Which process? A, with 2 units, right. So I'm going to put here A. I didn't click, obviously. I didn't click. I'm trying to use overtype, so I don't have to use backspace. Okay, and then here is going to be D, and C will still be there. So basically we restart, and there's nothing at level 1 now because E's done. So we start level 2. And we know we're only going to give it 2 units, but it only needed a total of 4 CPU units to begin with. So it got its 4. So it left. So what's next is we're going to start up D. C remains the same. And D needs a heck of a lot of units. D needs 7 units. So it got 2 of them here. It got 1 here, so we need to put D here. And C is still here. So that's 2 units. Unit 10 and 11, but at this level it's 3 units, so it doesn't time out. So we have D here and C here waiting to come in, and now it times out. I put it in the wrong place. It's got its 3 units, these 3. So it would time out and get placed at the end of level 3, right here. But we always want to show a process. As long as we have a process, we want to show one executing. So C would be executing. D would be in the ready queue for level 3. And C needs just 1 unit. So it's done. Now let's count how many units D has had. So D's had 2 right here. 3 there. So that's 5. So it would still be needing more units, and it would be there, and that would be the end of this example. And it still needs 2 more units, and if nothing comes in, this level is level 4 units, excuse me, level 3 has a quantum size of 4 units, so it could theoretically complete as long as nothing comes in ahead of it during this next 15 and 16. Let me count that up to make sure. So we have 2, 3 is 5, 6, 7. Yeah. Matter of fact, in the very next unit, it's going to be done and won't be anything in the queue. Okay, let me go back to your question. At cycle 5, this is cycle 5, D is after A because it timed out up here at the higher level, correct? Yeah, the queues run from left to right. This is last in. This is the first in. So we do it first come, first serve. A came before D at this level. If it is interrupted, it would have been before A. No. No. Cycle 8. At cycle 8, A was executing at 7. A was executing, and it would have gotten the CPU again, except E came back. E entered the queue. E entered the queue here and preempted A. And so we push it to the front of A of this level because it didn't get its full quantum yet. Okay? So I'm missing the question. I'm sorry. I'm missing your confusion. Okay, let's look at cycle 4. So at cycle 4, if D is interrupted, it didn't time out. It got interrupted before it got its 2 quantums. Then it would have been pushed. It would have been pushed in front here with a 1 left, and then what came in would be right after it. That's correct. Okay, very good. And this leads us to another concept, which I'm going to kind of illustrate in a second. But I wanted to see if what we did was correct. So I'm going to open up the completed one. wrong one. Okay, that looks like it. Yeah, we have a little note here. A got pushed with the quantum left. And then A got back in, D got 3, D, C, and then D. Yeah, this is exactly what we just calculated. Okay, I want to stop. Any questions on this? It's critical that you understand how to process this when you see it on the test. What's going to change on the test will be the rules. The rules will change, like the quantum size might change, the amount of CPU units needed by each process, where and I'm going to have like an E or an F or some process entering. It may not enter at 8, it may enter at 12, who knows. But you are going to have to understand how to process that. Because I think if you follow this and understand it, then you really get a good feel for what these cues look like. Okay. And I will review these again on next Thursday before the test. The test is open next Friday. Okay, Chapter 6. I'm going to go through that with you because each one of these chapters is a continuation on the next kind of issue involved with process management, and it's called process synchronization. And this is a critical piece, and you'll see it when we go through it. So first we'll discuss the background. We'll go through what's called a critical section problem. We'll go through a solution. We'll go through the concept of a hardware synchronization. We'll discuss semaphores, some classic problems, and then we'll discuss monitors. And at the end of the discussion of monitors, I'm going to illustrate a question that you'll see on the test, very much like I just did with the multi-level feedback cube. Synchronization examples and the concept of an atomic transaction. I checked Chapter 6 homework questions, and this is one of them. There's a few other in here in the Chapter 6 homework questions. So, our objective is to understand the critical section problem. We're going to present both software and hardware solutions and introduce this concept. Okay, so the background. Okay, first of all, concurrent access to shared data may result in inconsistency. Maintaining data consistency requires mechanisms to ensure the orderly execution of cooperating processes. And this is true in any time you write programs that do multitasking, or you have threads, different threads accessing the shared data. You know, they can do that in programs. They can access the shared data. You have the same issue as a programmer as the operating system does to maintain its tables. And I want to go back to the notes to make sure that you're following this concept. You have to maintain the data structures in the operating system. Remember, we had a system pointer, and in that system pointer, it points to all the data structures in your operating system. your process control block, and it has task control blocks. You also have ready queues, execution queues if you have more than one processor. You have wait or block queues. You got all these data structures. Okay? And you might have parts of your operating system, kernel threads, running at any one time and then being interrupted by some other process. So remember, we're interrupt driven. It's right here, asynchronous environment. We're interrupt driven, and we have to maintain these tables. So if we have multiple operating system kernel threads, updating the tables at the same instance of time, we will have all kinds of issues. So what we have to do is we have to synchronize the updates so that we keep these data structures consistent. That's the concept. Is that clear? Okay, very good. And the example is what we're talking about. Suppose we wanted to provide a solution to the consumer-producer problem that fills all the buffers. We can do so by having an integer count that keeps track of the number of full buffers. Initially, the count set to 0. It is incremented by the producer. Okay, there's a process, okay, or a little kernel thread. After it produces a new buffer and is decremented by the consumer after it consumes the buffer. So basically, after I stick something in the buffer as the producer, I bump the count up, and then when I take that count and the consumer takes one off, I decrement the count. And so I have a variable that both producer and consumer are going to access. This is called shared data. So I'm not going to go through the code of this, but we'll see what it's really doing. This is what the code breaks down to. So when you see something like count plus plus or count minus minus, that's a high-level programming language, and when the compiler produces it in machine code, it might take the variable count, store it in register 1, increment register 1. Each one of these is a separate machine instruction. Increment register 1, and then store the results of register 1 back in memory. Okay? And the count minus minus could be similar thing. The variable count gets stored in another register. The register gets decremented, and then the register value gets stored in the variable. The ALU is the addition or subtraction. That usually happens in the arithmetic logic unit. Okay, so let's consider this. And remember what I said on Tuesday. This is really critical. You cannot predict the runtime characteristics of any process. That includes the operating system processes. So, here's a consumer. S0 is the consumer here. Oh, and this is, I guess, we're on a single processor here. It's more complicated on a multiprocessor. But let's say S0 is the producer. It executes this, where the count goes into the register, and it's a 5. Then the producer not the output. I don't want to say the output. I want to say the runtime characteristics. How much of the CPU it's going to be getting at any one time. It could affect the output. And in this case, it will. So we have the count going into a register. We increment the register. We now have 6. And we stop the producer. Okay, we can do that. The operating system stops the producer and says, hey, it's time for the consumer. So the consumer starts up, and it executes the count, which is a 5, and it puts it in register 2, and then it executes the next statement, which subtracts. Now it's a 4, and now we stop the consumer, and we start the producer, because we cannot predict when these things are going to be executing. The producer stores register 1 into the variable count, and now we have 6, and then it stops, and we start the consumer, and it executes its next code right here, which stores its value of 4 in count, and now it's wrong. And that's the problem. That's called a race condition. And this is the primary issue of multiple pieces of code touching shared data. And once again, go back to this. This is data structures that are being shared by all the different pieces of the operating system, and it can be running concurrently on any of these. You guys see the problem? Am I describing the issue here? Databases really have this issue as well, just to throw that out there. So, solution to the critical section concept. You need the concept of a critical section. I don't know why he didn't describe that. Looks to me like he didn't really describe a critical section. But let's see if we can put these little things together. Okay, this is the primary assumption. Assume each process executes at non-zero, and no assumption concerning the relative speed of end processes. See, you can't predict these things. Okay? So first is something called mutual exclusion. So if process P is executing in its critical section, then no other process can be executing in their critical section. What we're doing is we're introducing the concept of a critical section. And maybe it's easier to see here in my example. Okay, you cannot predict the execution of any piece of a program, including the operating system. You're in an asynchronous environment. So, program A goes into a critical section. It updates the shared data, reads the shared data, updates it, stores it back, and A executes or exits the critical section. So the idea is we have a concept called critical section, where A can enter the critical section, update the variable count in this case, right? So this could be the producer, add to the count, store it back. Then B can go into its critical section. B could be the consumer, updates the shared data. In this case, it reads the data, subtracts 1 from it, and stores it back, and exits its critical section. So the idea is when I have a critical section of whatever it is, code or something, only one process can be in the critical section at a time. And that's what makes this work. That's the definition of a critical section. It has these characteristics that he's talking about. It has these characteristics. First, there's mutual exclusion. Okay, meaning if process P1 is executing in its critical section, then no other process can be executing in their similar critical section. Okay? That's mutual exclusion. It's a key concept. Questions? On the stopping of a thread, I'm not sure on that one. You can always stop a thread. It's just you don't know when it's going to stop. Yeah, it's called mutex. That's correct. But we're going to talk about how you implement it. Okay, second concept of critical sections. There's many concepts here. Progress. If no progress is executing in its critical section, or no process is executing in its critical section, and there exists some process that wish to enter theirs, then the selection of the processes that will enter cannot be postponed indefinitely. Okay? So the concept is, if you don't have anything in the critical section, no process, you don't want to postpone a process indefinitely that's waiting to go into its critical section. Okay, another concept is a bounded waiting. A bound must exist on the number of times that other processes are allowed to enter their critical section after the process made a request to enter its, and before that request is granted. So you have a count kind of concept. Okay? So these are three different ideas, and they're kind of intermeshed with trying to solve what the heck a critical section is going to be. There's several different methods used to do this. One is called software. You actually use the computer's software to do this. Well, I mean, all the solutions are going to be software, but this one uses flags, where it has a turn number and then it has a flag. Okay? So the flag array is used to indicate if a process is ready to enter its critical section. So this flag array I is true, implies that P1 is ready to go in to its critical section. And this is kind of what it would look like. So flag I is true, turn is J, and then while flag I is true and turn equals J, it drops into the critical section, does what it needs to do, and when it leaves, it turns its flag to false. Okay, and this loop is just continuous for each program, each process. So what we're saying is all the PIs would use this same structure, same code. Okay? And that would work, but it's not 100% efficient. Next. And this is what most systems have to handle synchronizing these asynchronous events. And each CPU has an instruction like this. Okay. If you're on a one processor, right, a uniprocessor, it's possible just to disable all interrupts. And then you know you're going to execute without an interrupt. Okay? But that's not very efficient, because you may miss interrupts. It doesn't really work well on a multiprocessor system. So what they've instead had is this concept of special hardware instruction. It's called an atomic hardware instruction. And it's either test memory and set a value, so it's called test and set, or swap the contents of two memory words. When I was on the mainframe many years ago, IBM implemented this test and set. I believe Intel has the swap, Intel processor has the swap concept. I'll talk about both of them, but you need to know these because they're going to be on the test. You need to understand them and know how to work them. So let's take a look at it. It's hard to see that with that colored background. I don't even like that. What he's trying to say is we're going to use a lock. So this is a generic concept. We're going to use a lock. So basically we'll say acquire a lock. If the lock gets acquired, we are in the critical section. And then we release the lock. And then we do the remainder. And all the processes would have this code in them. So if there's shared data that's being updated in the critical section, then you would acquire a lock, go in, release the lock, and some other one could be waiting for the lock to be released. We'll talk about that in a second. Tell me if I'm losing anybody. And this is a good example of a lock. This is how you would implement a lock. So I do test and set, Boolean, target, and I set my target to this Boolean value. I set it true, and I return the value. So basically, what the test and set does is this. Okay. It reads a variable, and it's usually Boolean, true or false. It reads the current value. It's going to return the current value, but while it's reading it here, right, it's reading the value, it's setting it. No matter what the value is, it sets it to true. So when we get back, the value returned is false, but the target now that we're looking at is true. Okay. See if I can explain it even better. I think he has an example. That's how you would implement it. Yeah, this is the use of it, and it makes sense. So let's look at that. So we have this Boolean lock variable. We initialize it to false. While the test and set reads the lock, it's going to return false because it's set to false. So it's going to set to false. So it's not true, so it's not going to do the loop. It only loops here while the lock is true. So the first time it's false, so it drops into the critical section. But now it's true. So the process got in, but the lock read it, returned false, but set it to true, all in one machine instruction. It's uninterruptible. That's the key concept between this. Is why this works. Is because it's one atomic, uninterruptible machine instruction. In other words, it does sets the value and returns what it was before it set it to truth. All of this occurs in one machine instruction. Uninterruptible. Key concept. If this was interruptible, we would have garbage again. Okay? So now let's see, while this guy's in, let's say this guy's in doing his thing, another process comes down and does a test and set. Well, it's going to return true. All right? It's going to return true because it's set to true right now. And so it's going to loop, keep testing and setting, and this is called a spin lock because it's spinning around and around and around and around. And there are many spin locks in the operating system. You want to keep these to a minimum, but there are quite a few. So you are spinning, waiting for the lock to become false. So the other process is finally finished with updating whatever it was updating. It sets the lock to false, and the one that was doing the test and set hits the false now, and immediately it's flipped back to true, but because it returned to false, it drops into the critical section. Is that clear, everybody? Anybody confused? Hi, Kang. I didn't see you come in. Who else came in? I saw Steve earlier. That's, Kang, that's the process of this instruction. Let me see if I can show you differently. Okay, the test and set instruction reads the memory value, so it'll return the current contents. Think of it as a function. It'll return the current value, but then it sets it to 1, basically, true, in one uninterruptible instruction. So, here's an example. I set this Boolean myCheck to false. Process A, do while test and set myCheck. What it's going to do is it'll return the false, and it sets it to true, all in one machine instruction. Okay, now because it's false, it enters the critical section. Okay, it's working in here now. myCheck is true because myCheck set it true. So once again, A is in its critical section doing the update. B comes along, uses the same shared variable, and same code, do while test and set myCheck. It's going to return a true, and because of that semicolon, it's going to be looping. It's going to be looping, looping. And what it's waiting for is for the myCheck to become false. Well, when A finishes, it's going to turn myCheck to false. Then the next iteration of this loop here is going to find that it's false, but immediately turns it back to true. So now B can enter its critical section and do its thing. I want to stop. I mean, is this clear? For everybody. Anybody confused? Steve, how you doing? Oh, yeah. Doing good. Okay. Mega, is it clear? Oh, you said yes. Kang, is it clearer now? Okay, it'll keep getting clearer as we discuss it. It's a very important hardware instruction, the test and set, or swap. Without it, you can't do this. We would not have a good operating system without that instruction, because you can't lock. If you're going to update data, you need a mechanism to basically synchronize any process that wants to touch that shared data. Now think about the dispatcher. Think about the I/O control handler, the service request handler. All these operating system handlers are pieces of code that want to touch the process control block status. It wants to touch the data associated with the operating system. Well, to synchronize all of these events, you have this lock mechanism that only allows one guy in at a time to update that data, and then you would have the next guy and the next guy and the next guy, and that way you keep the data consistent. Okay. Critical concept. Okay, swap. You're passing two variables to swap. So you save the contents of A in a temporary variable. You set B to A, and then you set this temp to B. So basically, you're swapping those variables in one machine instruction. Okay, and you can use this for a lock as well. Let's see how we do it. So we have a key. So our key is the shared variable lock guy, and we set the key to true. While the key is true, we pass the value of lock and key. So we swapped it, lock and key. If we get back false, the lock is false. Okay. Let me rephrase that. The lock is true. We swap it down in here, and now we're in the critical section. So while the key is true, we're swapping the lock. Remember, the lock is true or false? Okay, the lock is true or false. So we're swapping the lock's value with the key. While the key is true, I didn't catch this semicolon. It's doing the swap. Okay? While the key is true, we're doing the swap, waiting for it to become false. And it becomes false when we set the lock to false. Okay? That's what makes this work. So our key value is, we pass it a true, we flip it with the lock, and it's now false. A little more, to me, this is a little more complicated to understand than the test and set, but it works the same way. That's the same concept. Okay, so if we're trying to implement a bounded waiting mutual exclusion with the test and set, we have any number of processes that are waiting. That's what the array is. We set our key to true. We do while the waiting and the key is true. We do test and set on our lock, just like before. Okay. If both are true, or excuse me, if one of them is false, then we come down and set this to false, because now the lock, the key is false. So we set our wait to false. Remember, we set it to true up here. Wait is false. And we enter the critical section. And then we determine which one runs next by doing this calculation. And now we're waiting for this guy to come and run. And it's the same concept. So it's basically going through each of the wait list, if you will. I'm not going to have this kind of thing on the test, so you don't need to worry about that. I want to go back, make sure I covered. This is why you need the critical section. It's because you're using shared data. Each of the different processes or operating system kernel parts or operating system handlers, all of those little pieces of code can run and get interrupted. Okay? Or they could run on two different processors, right? And you don't want, if one processor is updating the data, you don't want the other one to catch and update something differently. So you need the concept of critical section. And to implement the critical section, you need the concept of either swap instruction or a test and set instruction, where two things happen in one uninterruptible instruction. That's the key concept of this machine instruction. Okay. Because then you can implement code to do this kind of locking. This is a spin lock. It stays here while my check is true. It stays there while my check is true. It keeps reading the value of my check and setting it to true. It reads the value, sets it to true. Reads the value, sets it to true. Finally, we set it false here, and then this guy may be waiting for this, reads the value, it's now false, and it can go in. But as soon as it reads false, it's set to true. So if this guy comes up and it's true now, it's going to stay in this loop until B turns it back to false. It's cool. It really is a cool concept. All right. This next concept is a little more weightier, but let's see if we can go through it. Synchronization tool that does not require busy waiting. Okay, now, what is busy waiting? A spin lock is busy waiting. You're running CPU instructions here, waiting for this thing to become false. You're waiting, 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 and waiting, and waiting, and waiting. That's busy waiting. Is that clear, everybody? Yeah, the CPU is kind of just being wasted. Nothing's really happening. And that's what they're talking about. It does not require busy waiting, but it does require some other concepts. It requires an integer variable. Let's say that. And you have two standard operations on that variable. One is wait, and one is signal. Okay. Originally called P and V, because these came out of Scandinavian countries that developed, Scandinavian countries that developed the signaling for ships, because ships needed this to communicate with each other, and they used this P and V concept with flags. Okay, and that's where this concept really started. It was with shipping, and then it went to trains, locomotives, and stuff like that. And then, of course, computer science people picked it up and used that. But now it's called wait and signal, P and V. This is less complicated. It can only be accessed via two atomic operations. In other words, these operations do not get interrupted. Okay? So let's see what happens. We wait S. While S, the count, is less than or equal to 0, no op. No op. So we're staying in this loop here. No op. S, we're subtracting S. If it's greater, then we subtract S from S. So basically we're counting down. Okay? Signal S says we increment S by 1. So when I need to wait, I call wait S, and I will signal S when I'm got something available. I think a better usage of these concepts is going to follow to make more sense. That's hard to see. Accounting semaphore. Let's put it in notes. I think it's easier to see stuff when you have an example. Okay. I want to, I have, let's say I have 3 CD devices. All right? I have 3 CD devices. And I want to keep track of that. So I have a device number. So CD number is my variable that I keep track of, this thing, and I've got 3 in it. Okay. So I want to allocate one of the CDs. Okay. So to allocate, what I do is I say if let me think of it this way. If CD number is less than or equal > 0, then I wait on CD number. I put it in that wait. And then, so now it's waiting. And what you don't see here in this diagram is there's a queue involved. CD has a usage of that. Yeah, I think this is better. So you've got your value. You're going to wait on your semaphore, whatever your semaphore is. You wait on that value until there's something to have available. Okay, and then you signal when it is available. You signal the semaphore, and that increments the value, removes the process from this list. This list is the wait queue. It blocks the process. It blocks the process. So I need this special queue. So to implement it, I need a count variable, a value, and I need a queue. So once again, over here, I have my count variable, that's my CD number, and if it's less than or equal to 0, I wait. Basically, I put it on the queue. So let me say this process, whatever it is, PI, would go onto the wait queue, that list. Okay, that's an allocation. Else, I got to have an else. Else, what I'm going to do is I'm going to decrement the number of CDs I've got. So I decrement the number, and I give one of the CDs to that process. I'm allocating it. And that ends, I'm writing in VB code. This is VB code, what VB code would look like. So if the count is less than or equal to 0, then I put it on my wait queue in my semaphore. Else, I would decrement the count and give one of the CDs to that process. I would allocate it. And that's allocation. Okay, deallocation. Deallocate one of the held CDs. So the process is going to do the following, right? It's going to signal that a CD is available. So the signal does the following. So let's look at signal. And I'm doing it the way, sort of like close to the way the book is doing it. So on a signal, it's going to check the wait queue. If any exist on the queue, assign that waiting process the CD. Okay, so that would assign it and allocate it to that. Okay, else, I should put my then here. Okay, else, decrement, so basically CD, our increment, CD number plus 1. And that's the way it would work. So once again, I think it's easier with this example. You have a semaphore associated with the number of CD devices, and you're going to count down to 0. So if you are 0 or less than, because you could be, I guess, less, then you place that process on the wait queue associated with that semaphore. Else, in the allocation, you would decrement the number because you have one. You would decrement and give one of the CDs to the process, and it's gone from the request. Now it's got the CD, it's got to deallocate one of the held CDs. So it signals the same semaphore that it's available, and in the signal, the purpose is to check the wait queue. If any exist on the queue, then assign that waiting process to the CD, assign that waiting process, that CD, I should say, that CD, that just became available. Else, if there's nothing waiting for that, you would add 1 to the queue. So now you would have 3 again. And you see how this would work. Any questions? Okay. Well, that's what he's describing. He's describing that in this method. In his case, he's decrementing it before he evaluates it, which is okay, I guess, because we're in a wait. We're in a wait, so I guess you could decrement this value. But the whole idea is, if it's less than 0, you add it to the wait list for that queue, and you block the process. Okay, and the signal is to wake it up right here. So you add 1 to the value because it's coming back. You're signaling that it's coming back or available. And if you've got something less than, you want to remove the process from the wait list as it's negative, because you've got one sitting on there. Okay, that's how it could be negative here, is because you went to the left of 0 and you have many processes waiting. That's why they use it 0 here. And then you wake it up, and that guy either gets whatever it is it's requested, or access. I know it's a little more confusing, but conceptually it's what I just said. We keep track of a shared variable in both of these structures. Now, a lot of these things, semaphores today, could be implemented in hardware. There could be, I haven't looked at the latest Intel processors, but they may have a semaphore construct that does this for you. If not, you'd have to implement it in code. Okay, we're moving towards chapter 7, deadlocks. I really like this chapter. It's really cool. It kind of brings together everything we're doing, but we're introducing the idea now, okay? Because when you lock anything, right, you lock anything on your system, and you do the stuff that we've been doing, it's possible that no process deallocates. In other words, a process may get a CD and never relinquish one. Okay? Or I could have this situation. I could have 3 CDs allocated to 3 different processes. A 4th one wants one, goes on to the wait queue, and never gets in because these 3 are running, okay, and they might need a 4th one. So I have 3 different processes, but it's possible that process 1 here wants 2 CDs. Process 2 might want 2 CDs. Process 3 might want 2 CDs. Well, wait a minute, I only got 3. So it introduces the concept of a deadlock. That I've got a resource and I want another one, and that's this concept. Okay? And he's trying to illustrate it with the semaphores as to what's going to happen. And it's possible. And so you could get starvation. Question? You could get starvation. It's indefinite blocking. That's what I tried to illustrate. A process may never be removed from the semaphore queue in which it's suspended. And then there's priority inversion. Okay, it's a scheduling problem when lower priority process holds a lock needed by a higher priority process. So what happens is that lower priority process becomes really critical because it's blocking a resource of some kind. So those are 2 situations that we have to deal with. And we will in Chapter 7. These are examples of these synchronizations. We talked about the bounded buffer problem. The producer-consumer guy. Readers, writers, producers, consumers, readers, writers, similar. And then this dining philosopher's problem, which we'll try and do. Okay, so I could have a mutex semaphore starting at 1. Semaphore full initialize the value of 0. Semaphore empty initialize the value of n. I'm not going to really go through all this code, so I'm going to kind of skip it. You can look at it and see how it works. But it will work, okay? This will work. And readers and writers work nicely too. You can, at one time, you could have readers and writers, but if you have many readers, you want to have the readers be able to read, right? And they don't perform any updates, whereas writers can read and write. It's a little more complicated problem, but it's fun to look at. I usually did this in class with people, but I'll show you the concept. Is you've got these, let's say, chopsticks. Looks like there's 5 of them. You need 2 chopsticks to eat. So the idea is the philosopher's thinking, and then he says he wants to eat. So he grabs his left chopstick, and he grabs the right chopstick, and he eats. And then he puts them down. This guy, same thing, he grabs the left and the right. This guy too, the left and the right. Well, if this guy was thinking, let's just go through it. He's thinking, he grabs the left, okay, and before he could grab the right, this guy finished thinking he grabbed the left. So he's holding on to this chopstick. Okay, and before this guy could get the right one, this guy finished thinking and picked up his left. Okay, so it's gone for him, so he can't eat. He can't eat. This guy, same thing. He can't. Well, yeah, he grabbed the left, and he went to grab the right, but this philosopher grabbed his left, which took that out of his way, so he can't eat. And finally, this guy finished, and he grabbed the left, and so he can't get his right. And this guy already has his left. So basically, all the philosophers each have one, and none of them can eat because they need two to eat. And that's the dining philosopher's problem in a nutshell. It's the same problem that leads to deadlock. It's a deadlock. So you can code it up and play with it. Okay, monitors are a way of implementing a mechanism that your shared variables and can be executed in a mutual exclusion concept. Okay, that's the concept of monitors. So let me see if I can explain it. When I want service, by the way, a lot of small processors, what do they call them? Specialty processors. Like are in cars, refrigerators, microwaves, those kinds of processors wherever there's kind of not just pure code, but there's a little bit of an operating system concept, they would use a monitor to keep the shared data clean. So you have entry points, and you have a queue where a process can call an entry point, and then when the entry point is being serviced, it services that and only that one. So it services that one, finishes the service, or if it can't finish the service, it puts it in a queue. It'll put it in a queue to be serviced. So it either services it or puts it in a queue to be serviced later. So it does the same kind of idea of and it only does one at a time. I mean, it will only let one process in. It could have many entry points. Many entry points. Okay. I'm going to illustrate it better than this because you're going to see a problem on the test with 5 points that describes this concept. So you have what's called condition variables, condition X and Y, and you have a weight and a signal on X and Y. So a monitor with condition variables. You have your variables, it can get associated, and we have these queues. Okay. Works the same way. So we're going to have a weight queue inside the monitor. He's got it shown here, the weight queue. I'm going to skip that. I'm going to skip that. You can implement it with these concepts, so you can take a look at that. I don't like to spend a lot of time on the code. Doesn't really help, I think. But if you're interested, you can certainly do that. I'm not going to go through these because you may choose one of these for your project. Remember, you're going to have a team project, And at the end of next week, so beginning of, let's see, this is week 5. At the beginning of week 6, I will assign team members, and then you guys will work out which operating system you want to review, and you'll be answering questions about that operating system. I'll explain that in week 6. So I'm not going to do that. Okay, so let's look at the monitor problem. So I think you'll see it's a fun problem. Okay, so I'm going to illustrate a monitor. This is a monitor. And what its purpose is to allocate at E1, well, there's many entry points, and this is condition C1. And C1's condition is for printers. It looks like we're maintaining printers. So the idea is that process B enters through E1, and that it wants a printer. Okay. C has a printer and wants to release one through E2. So let's go through the notes. But this is the way monitors would work. Number of printers is the number of printers available. Okay. It allocates one of 4 printers, so we have a total number of 4, to a process when a process enters through entry point E1. It checks the number of printers. If it's less than or equal to 0, it cannot allocate a printer, i.e. they're all allocated. It places the process at the end of the awaiting printer list located at C1. If it's greater than 0, it allocates a printer and decrements the number of printers. So that's what happens if it comes through E1. Okay. Number 2 there, it deallocates one of the printers when a process enters through entry point E2. So it's going to increment the number of printers, because now one more is available. It ends by signaling condition C1. So this is implementing it via semicolons. 3, after a process has been serviced, it immediately leaves the monitor because it's got its thing that it needed. Okay, number 4, when condition C1 is signaled, if a process is waiting in the awaiting printer list, C1, it enters the monitor and will receive the available printer. Does essentially the code in number 1 above. Okay. All right, next thing is the monitor always services E2 before servicing E1. So it wants to always, if there's a process here, it wants to service that because it knows it's going to give up one before this one needs one. Okay? So that's why we have that rule. So look at the cues closely. Process A has just now entered the monitor. Describe the events that should follow. There are 4, and I supplied the start of the first one. Completed 2. If there are 3 cases, there are 3 cases to consider. I think I have the completion one here. I'll just show you the first one. Let's just do it a little at a time. This is on Canvas. So there are 3 possibilities. Process A could have entered from a signal, meaning a process we don't know about came in, deallocated one, and signaled C1. That's how it came in. Okay. Also, we know what the number is. We know what the number of printers is if I have anything waiting here, I know the number is 0. So A was here, waiting in front of D. So the number was 0 because it was waiting. Then some process we don't know about came in, deallocated, signaled, and that's how A came in. So we know the number has to be 1. The number of printers has to be 1. The only number it could be. Is that clear? You really need to understand the beginning. Where does the number start at? Does it start at 0, 1, 2? So you kind of have to look at the situation. Okay, so let's go through what it does. A enters through C1. Yeah, we just said that. It receives a printer because 1 was available. We decrement the number of printers. We must have just had 1. Now we have 0, and it leaves. So I want to stop. Is this these events? Do they make sense to you, or is anybody confused? It's a tough one to understand. I know that. Good. Good. All right. So, A left. What does the monitor do next? There's nothing here now. We handled A. A's got the printer and it's off doing stuff. What would the monitor do next? What entry point does it serve first? No, Mega. What does it say here in number 5? The monitor always services E2 before servicing E1. That's okay. But I want you to understand that, because I could switch them around on the test. Okay, so the next thing is C comes in, requests a printer. Is a printer available? Look at it. Is a printer available? What's the answer? No. So what do we do with C? What do we do with C? If it's requesting... Oh, I'm sorry. I'm sorry, that's not what we do. Okay. I was doing A. E2, C comes into the monitor, releases the printer, and increments the number of printers. Now, how many printers do we have available? Right. Good. 1. Good. Not 2. 1. Kane, do you see why it's 1? It's 0 here, and when C comes in and deallocates it, we increment it. Okay, and guys, and we signal C1. So once again, it deallocates through E2. Okay. It deallocates one of the printers, and it signals condition C1. It ends up, so we'll see that when we look at the next line. The next line is C enters through E2, releases a printer, increments the printer, it's now 1, signals C1. Okay, what happens next? What's the last thing it did? Okay, what happens when C1 is signaled? Right here. When condition is signaled, right. So which process is going to get serviced next? Right. So we know the number is 1. So what would happen would be D enters through C1, receives the printer, we decrement the number of printers, so there should be back to 0, and it leaves. Let's see if that's what happens. D enters through C1, receives a printer, decrements the number of printers, we're back at 0, and it leaves. So now we've serviced A, C, and D. We'll always service the 4, guys. So the 4 events we're always going to have is it'll service one of those 4 on each line. You got it. It's back to 0 now. Okay, now we got A done, we got D done, we got C done. What does the monitor do next? Well, it checks E2. Do we have anything on E2? Remember, C's gone. No. So it checks E1. Do we have anything on E1? B. And E1 means it wants a printer. And how many are available? All right. So here's the steps. B enters through E1, requests a printer, none available. What do we do when there's none available? Yes, it would be here. And what this thing would look like at the end of these events would be B would be waiting here, and we would have nobody here, and nothing being worked on in this particular monitor. And let's check it. B enters through E1, request printer, none available, placed on C1. Good. And now you see kind of what I'm expecting you to write for each one of these. All right, now, that's example A. There's going to be 3 examples because this process could have come through 3 different things. It could have come through E1, it could have come through E2. I showed this example here of it being from C1. But suppose we restart everything, right? We restart everything. As long as there are processes at E2 and C1, E1 will process never go through. It'll eventually go through. Yeah, it would eventually go through. But you're right. If there's anything on E2, it's going to release and signal C1. If there's anything on C1, it's going to come and get that. Until basically these guys that were waiting get serviced before this one that was requesting. See, this one's requesting. These have requested already, and they're waiting. So this is pretty fair. Okay, reset the situation again, and process A just entered through E1. Now I know that we service E2 through E1, but what happened was A entered through E1 and then C showed up. Okay, that's kind of what happened here. So this is what the environment looks like. A came through E1. Well, first of all, how many printers are available if we've got D sitting over here? Right. So if A comes in, what happens? A requests a printer. None's available. Where does it go? Right. It's basically this line right here, except it says A enters through E1, requests a printer, none available place. Well, let's see if that's true. Yeah. A enters through E1, requests a print, well, it should say printer, none available, placed on C1. Okay, so that took care of A. So now we have A after D, right? A after D in the condition here. What does it do next? E2. So the next guy should be what? What would happen? C enters through E2. Tell me what it's going to do. No, that's E1. No. Yes, Kang. It's going to release a printer. And we're going to increment the number of printers. So it's really doing this. It's doing this same exact thing. C enters through E2, releases a printer. We increment it. It's got 1 in it now, and signals C1. That's the same step, and you'll see it here. C enters through E. Wait a minute. Yeah, E2 releases the printer, and we're now at 1 and signals. Okay, what should happen next? No. Right, Dale. C1 was signaled. D and A are here. So what would come in next? What process would get serviced? D. Exactly. And it would be the exact same thing as this. D enters through C1, receives the printer, we decrement it, and it leaves. Let's check it. D enters through C1, receives the printer, we decrement the number of printers, and it leaves. So the only one we have left is what? Which process? Yeah. B enters through E1, requests a printer, you got it, Mega. None's available, and what? C1, you got it. That's exactly right. Excellent. Okay. B1 enters through E1, requests a printer, none available, placed on C1. So this thing ends up looking like this. A and B are sitting here waiting for printers. I may ask you, guys, which processes are waiting at the end of servicing the 4 here, which are waiting for printers or whatever. So, you know, just be aware I might ask that. Okay, the last case is going to be a little different. Are you guys ready? Yeah, King, let me read that. Just to clarify, each of the entry point will have a fixed interaction to printer request, release, receive. Yes, that's correct. And that interaction will never change. That's correct. What if there are no processes at E2, but there are processes at C1? Then nothing would happen, right? If there was no process at E1, E2, if there are no processes wanting to give it back, but there are processes that are waiting for it, anything coming through E1 is also going to end up here, and it's kind of a no-show. I'm probably not going to have that case. Because I'll always ask you to reset it, right? Reset and look at it. All right, so let's look at the last case. And it looks like I didn't fill it in. Well, that's good. I didn't fill in the last case. So let's do that. So, whoops, sorry. So what are we asking? Reset the situation. Enter through E2. Ah, okay. So A enters through E2, and what does it do? Releases a printer, increments the printer, and signals EC1. Exactly right, Megan. What's the number of printers right now after that happens? 1. Excellent. Excellent. Okay, so now what would happen? What's this next line? So yeah, what D enters through C1. That's right. Very good, Steve. Receives the printer, decrements, and leaves. Okay, that's number 2. That's number 2. What's the number of printers at the end of this? 0. Excellent. Okay, what happens next? F3. No. Bail, you got it. C enters through E2. And what does it do? Releases a printer. Good. Increments and signals C1. There just happens to be no process at C1 right now. Okay. Now, what's the number of printers at this point at the end of 1? Excellent. So now what happens? No, it's not C1, E1. Right. So what process? Start with the process. Yeah, I always start with the process. B enters through E1, that's right, Mega, requests the printer and receives it. You should say receives the printer as well. Decrements the count and leaves. That's exactly right, Mega. But you just need to add the receives a printer. Okay? Just like I did here, receives the printer, receives the printer. We know it's requesting a printer, but if one isn't available, you would say request a printer not available. But if it receives it, just say it receives it. Okay? You guys got it. Does this make sense now? And that's how monitors work. All right, you're going to see one on the test like that, and I'll review it again with you. Like I said, next Thursday night, it's my review night because there's a lot of material here in chapters 3, 4, 5, 6, and 7 that I want to make sure you understand. Ooh, yes we are. Thank you for reminding me. Oh, we got to have that. I thought I did that. My mistake. Let's do it right now. Thank you for reminding me. We got 5 minutes. It's just enough time. Okay, here's the question. our process state diagram didn't include a concept used in our rules of multi-level feedback queue. And Art illustrated this in the extra credit solution as to why this state is needed. It is called blank. I haven't demonstrated it yet, but it's in our notes. And it's right here. This particular example is illustrating what's happening. We started our bar none here for some reason. It was executing, it was in the execute state, but it didn't get all of its CPU. Remember the quantum we talked about? Right, the quantum sizes and the multi-level feedback queue. Where was that diagram? This here, this never got its full quantum, got interrupted. Well, what you're not showing here in this example is it's possible that some operating system interrupt was being handled when a process was running and didn't get its full quantum. In other words, it's not a multi-level feedback queue concept. It's a concept where a process was running but did not get its full quantum. Well, to be fair, you have to get its full quantum. And bar none did not get its full quantum. So what we do is we hold it. So it's called a held state, where we hold it, and then after we handle whatever the operating system needed to do, we dispatch it and we restart it. So the state is, it was executing, it was interrupted, but we're not going to assign any other process because the quantum wasn't used by this process. And we're not in a priority scheme. If we were in a priority scheme, then we probably would have a different concept for held. But held is a state. Does that make sense? Oh, good. So let's try held. And it might be hold. Oh, God, if it has quotes in it, I'm in trouble. Let me edit it. This is that same issue of going from catalyst to canvas. Let me look at that. Yeah, I gotta get, it's those asterisks. Let me get rid of them. I'm sorry, I missed that when I was reviewing this quiz earlier today. So let me update it. You could have, I guess, put in the asterisk, but no, let's just use the word. Okay, resubmit. Let me check, see how you guys are doing. Steve, try yours again. Let me refresh. There you go. Okay. Meg, I got yours, and Gang, Steve. The rest of you guys can do that. Looks like it's going to work fine. Okay? All right. I want you to have a great weekend. Enjoy the Super Bowl. Thank you all for participating. You guys are really good. Go Pats! Hey! Woo! My wife has Pats loafers or something. Flip-flops. Good night, guys. Thanks again.